So welcome again, guys, to Support Vectors Meetup. This is August the 9th. It's a Friday. This is the last of our last in the series of talks we are giving, titled An Intuitive Introduction to Machine Learning / AI. So far, we have covered the topics of machine learning itself. What is machine learning? Why is it relevant? Then we covered correlation, causation, sequentiality. We covered regression and regression towards the mean. Then we covered classification. We covered clustering. And today we are going to cover dimensionality reduction. This is the last topic I would like to cover. With these four topics, you should have a broad and intuitive understanding of this field. Now, a couple of bookkeeping things. Many of you email me or write and say, you missed the session. Can I have the recording of the meetup session? So please be aware that all our meetup sessions you can, amongst other places, based on your favorite social media, LinkedIn or whatever, you could go to Support Vectors LinkedIn channel and see it. You could go to Support Vectors Twitter channel and see it. But I suppose it would be easiest if you just came to Support Vectors YouTube channel and go to the live, and you will find that all the past recordings are here. In fact, close to 500 videos, all of them live recordings of our sessions, are posted to this to our YouTube channel. So you're most welcome to go back and check with me. Now, indulge me in 2 minutes of advertising. Support Vectors is an AI training organization. We provide fairly in-depth, hands-on training in AI. We are based on a certain educational philosophy, which is to be a high engagement place. We believe that learning has a huge emotive and social component to it. So we have a real on-premise learning. People do it also remotely, but we do it in teams where you learn a lot from your peers and you learn a lot from the faculty that we have. We have a pretty good faculty of very people with a lot of industry experience in this field of machine learning, and not people who have just learned the subject last year, but people who have known it for 2-3 decades. So you're most welcome to browse through our course. I would like to invite you to do that. From next week, our formal courses are going to start. If any of these interest you, please do register for that. In particular, the 2 ones, Introduction to AI, it gives you a broad-based understanding of all topics in machine learning, and especially the neural architectures. We do about a dozen important neural architectures. It spans 4 months and is a very thorough course. We meet twice a week for 3 hours each. Then, the other course that people use as a foot in the door is the Large Language Model Projects Bootcamp, LLM1, in which from day one, you form little teams and you build something real. On the first day itself, you would build an AI search engine. And from there, you would continue to RAG, to multimodal learning, to computer vision, to document AI, to guardrails, and pretty advanced topics along the way, diffusion models and so forth. And we do it at the level of building some real world products, as well as on the theory side, reading through an explanation of research papers, the foundational research papers on the topic. So if that interests you, you're most welcome to register. In fact, I hope you would register. And that ends my 2-minute advertisement for Support Vectors. I would now like to get back to our main topic. Now, this series was broken up into 2 parts. One, what is called predictive modeling, or where you predict something, you build a model to predict something. For regression, you predict a number. For example, how much ice cream would an entrepreneur sell on the beach, given the temperature? Given the age of a child, what is the expected height? So you're predicting a number, that's regression. The other kind of predictive model predicts or identifies a type. If I were to give you certain parameters of an animal, let's say height and weight, would you be able to identify and tell whether it's a cow or a duck? So that is classification. You're not predicting a number. You are identifying the type from a finite set of types, from a finite set of classes. Classification and regression have been the workhorses of the industry, and together they form predictive modeling, or as is often called, supervised learning. It is called supervised learning because you take labeled data. You have to give an example for the machine to learn from and to generalize from. It's like teaching a child. You take the child to a meadow and you show a duck. You explain that the duck is small and is feathery, has beak, has webbed feet, and that's a duck, and that too is a duck, and so forth. Give a few examples of ducks. And then you show a few examples of cows. And as you show examples of cows and ducks, if the child learns to generalize from those examples, grasps the duckiness of a duck or the cowness of a cow, the concept of a cow and the concept of a duck, you feel that the child has learned. And the evidence of that would be you show a new animal, which is a cow or a duck the child has not seen, and you ask the child, what is it? And if the child correctly identifies the animal, you now rest assured that the child has understood what a cow or a duck is. In the child's mind, there's a concept, a model to identify cows and ducks. And so with machines. When a model can do that, you say that the model has learned that. So those are algorithms. They're called supervised learning algorithms because they learn to generalize from examples. That is one kind of machine learning. There is another kind of machine learning which is called pattern recognition. Actually, there is a third kind which is called reinforcement learning, which we didn't cover in this small series, but we'll leave it for later. I will be covering those things in our usual Wednesday weekly paper readings. But in pattern recognition, the goal is not to predict anything at all. The goal is to identify patterns in the data. For last week, we did clusters. When you observe that the data as it presents itself to you has clusters, right? It comes in clusters and a few outliers, then to discover those clusters is a form of pattern recognition. And clustering is the process of discovering clusters. We also talked about that clusters are far more prevalent than you think. Most data is generated by physical phenomena, or biological phenomena, or financial or economic forces. Most generative forces, most forces that cause phenomena to happen are nonlinear forces. Whenever there is nonlinearity in nature, you will often find that the consequent data or the phenomenon, data or the observables of the phenomenon will exhibit clusters or non-uniformity of the data. They can therefore be treated for cluster discovery. So that is clustering. We covered a few algorithms of clustering. One of them is to look at it as a physicist, to treat as though every data point is a little steel ball, and therefore wherever data is clustered would be rather heavy, dense areas. One intuition I gave you is if you think of it as all the steel balls on an elastic membrane, on a stretched out rubber or elastic membrane, then wherever the clusters exist, you'll find depressions. And in a way, therefore, intuitively, to find clusters or to find those valleys in the elastic membrane. So that is one way, that's a density-based clustering. Another, much more simpler and more prevalent method is k-means clustering. It answers only half the question. It doesn't tell you how many clusters there are, but it says, tell me how many clusters there are and I'll find it. So suppose you say, find two clusters, it will take two random points and declare them to be the cluster centers. And then it will go through an iterative process by assigning each point to the nearest clusteroid, the centroid, and then knowing that that assignment may be wrong, then re-updating or recomputing the centroid. And through that iterative process, as we saw last time, you end up discovering the true clusters most of the time, though not always. K-means clustering has certain limitations. But one of its limitations is, of course, the dimensionality problem in higher dimension spaces. It does poorly, but more importantly, it suffers from the problem that when the data is not globular, does not admit a very simple convex hull, it actually fails quite badly. So then density-based clustering or other methods work better. We also talked about agglomerative hierarchical clustering, which is a way of saying that, well, let's start with each point as a cluster. And if 2 points are very near, we'll merge them together. And then you successively do that to create a tree called the dendrogram, very popular in medical sciences and biology and many, many fields. It has the advantage that you can pick and choose how many clusters you want to see based on the level of resolution you want to see the clusters at. So this is it. One question that comes up is, what is the right clustering algorithm? Which is the best clustering algorithm? As with all machine learning, the no free lunch theorem holds, namely, there is no such thing as the best algorithm or the worst algorithm. Our algorithm is either useful or not. And the no free lunch theorem says that for every type of data, there would be a different algorithm that would work best. So based on which data you're looking at, any one of the many clustering algorithms may be best suited to it. You can't say that a priori, you can only experiment and see which one does work best. Having said that, k-means is perhaps being the easiest one. It's quite often the first line of attack. And when that doesn't work, then people escalate to other clustering algorithms. So that was clustering, a form of pattern recognition. That summarizes what we did yesterday. What are we going to do today? We are going to do a new form of pattern recognition called dimensionality reduction. So what does dimensionality reduction talk about? Suppose, and let's give an example, you are looking at three-dimensional space. In the three-dimensional space, nevertheless, there is a road, and let us say that there are different things growing, there are trees growing, there are things happening. You realize after some time that most things of interest to you, let's say that you're looking, let's be very specific, people. You happen to observe that most people are on the surface of the earth. They're not generally flying around like satellites. They are not burrowing into the sea or the land. Most human beings are somewhere proximal to the surface of the earth. They might be at most 1 story high or 10-story high building, but as far as looking from space is concerned, you could probably approximate it and say that people are all on the surface of the earth. So let's take that as an example and build upon that. Suppose you knew you were an alien and you had just come to this planet. You would not have an idea, and let's say that you had just received some of the messages that SETI or any of those alien searching programs has been constantly beaming into space. So here you are as an alien, and you are looking, well, God knows if aliens have 2 legs. Maybe we'll give them, here's your alien. And this alien comes to Earth and is looking at a three-dimensional space, of course. And here is your Earth. This Earth is approximately spherical, bulging a little bit, not exactly spherical, but we'll take it to be approximately spherical. This is your equator. And it has hills and valleys, some high places and some low places. And you're looking for people. Imagine that you have a detector of human beings. You may find that, and now I'll take a little area of the Earth, a place of the Earth, and let's say that there are some mountains and there's plains, and you find that there are people all over the place. Occasionally, there are people perched up in their mansions on the hills, right, or hiking. And occasionally, you find that people are scuba diving. All of that is happening. But when you look at it from the distance to the Earth, you could say that, yes, look very precisely, human beings are living. If you looked at where they are planted, they live they're embedded in a three-dimensional space. But it would be a fairly good approximation to imagine that they are actually living on the surface of the sphere, on the surface of the Earth. That would not be a bad approximation. Would you agree, guys? That when you look at it from the distance of a million miles away, the fact that you have one story above ground or 2 stories above ground looks like a very minor and inconsequential perturbation in the data. And so you could imagine that people are just points on just the shell of the Earth, just the surface of the Earth. Would you agree with that?
Makes sense.
So, yeah. So to do that approximation, to come to that realization that actually, to the first approximation, they live on a lower dimensional space, not in three-dimensional space. The surface of a sphere is two-dimensional, isn't it? An ant can walk all over the surface of a ball, right? So you can say that people who you thought were living in three dimension were actually, simplified view, they actually live in two dimension. Actually, more specifically, they live on the surface of a sphere. Right? S for sphere, a two-dimensional sphere. Right? On the surface of the Earth. So to discover that, to find that observation is a form of pattern recognition. This is pattern recognition. Obviously, you discovered something. That discovery is worth it. And in particular, this pattern recognition is called dimensionality reduction of the data. That's a pretty formal term. But what is the dimensionality reduction? You thought people are all, in the absence of any information, you would assume that people, if you come to a planet, they would be all over the three-dimensional space. And yet you discover that human beings, for whatever reason, they seem to be sticking to the surface of the Earth. And that pattern recognition is a form of dimensionality reduction. You realize that they don't exist in three dimensions, but they actually are planted squarely on a two-dimensional surface. Right? You can take another example to illustrate this point. Imagine that you have a plane. And here you plant a lamp. And the lamp is projecting light. If I were to ask you, or maybe three-dimensional also. Now, if you have grown up in a developing country, as I did many, many years ago, we used to have this lanterns. And these used to be typically kerosene lanterns. Even today in US, people who hike tend to carry that sometimes. People who go hike and camp, campers do carry kerosene lamp. So imagine that you are in a deep dark place. One thing that becomes premium is the light from a kerosene lantern isn't too bright. So if you want to read something, how much light you are getting at place X, A, let me say point A or point B matters. Right? Let's say that you are trying to, yes, suppose you're trying to read a book, let's say, or read some instructions, some survival manual, and you're camping in the forest. You would agree that you would need to be pretty proximal to this light in the dark to be able to read it. Right? So you can say that the luminosity, let me just create a function without going into the physics of it, luminosity, or think of it as how bright the light is, and write it as L at a given point in space-time, space. This is X, Y, Z axis, let me just put it, X, Y. It's a function at every point in this room or in this space, in your little camping tent. At every point, there would be a certain amount of brightness of light. Right? So there is a value that is here, luminosity. But you would agree that, and this luminosity, if you think a little bit about it, it is actually very directly related to not three variables, X, Y, and Z, but actually related to only one variable only. Can you guess what that is?
Just the distance.
Literally, the only thing that matters is suppose you're here, even if you're a fly here, the only thing that matters is the distance d, right? So it is actually a function of just the distance d. Okay, luminosity is simply a function of d.
Almost like inversely proportional distance square or something like that.
That is true, but we won't get into the specifics. Suffice is to say that we may say that luminosity was initially a function of 3 dimensions. So from 3 dimensions, for every point you could give a luminosity. But if you think a little bit harder about it, you realize that actually luminosity is not about 3 dimensions. Oh, what just happened? This is something that OneNote does, and usually when it does, I have to kill it and start all over again. Apologize for this technical difficulty. Okay. For whatever reason. Give me a moment, guys. I'm having, whenever this happens, I find it helps to restart OneNote. All right, let's try a luck. And hopefully we have better luck. So initially, for every point X, Y, Z in space, you could give a number, luminosity, certain value. But as you think about this data, if a machine could determine that no, all you need to do is, suppose that you look at the location of the light. Let's say that the location of the light is at X naught, Y naught, Z naught, some coordinates, X, Y, Z. it could determine that d, which is equal to, or let's take d square, which is equal to x minus x naught. This is just the squared Euclidean distance, y minus y naught squared plus z minus z naught squared. That this is the only thing that matters, because luminosity, if you could create this variable d for every point, now what happens? Now what happens? You can say that luminosity is just a function of d. D is a one-dimensional, is a number. It's just a number, isn't it? Distance is a number. And I can say a luminosity is just a function of distance from the source of light, which is most intuitive. And therefore, this brings up the question, can machines discover that? Can machines look at the data and infer and discover this relationship? Wouldn't that be wonderful if it could do that? The fact that machines can do that is quite remarkable. And this is again a situation of dimensionality reduction. What did you do? You took data, let's say that you had measurements, a table of data, X, Y, Z, and luminosity. What you did is you reduced it to a table with just two columns, distance and luminosity. Isn't it, guys? So you have some values here. And now, same number of data instances. The magic is you discovered the function, the D relationship that simplifies, greatly simplifies the understanding of the data. Now, one thing I want to emphasize, this is not just blind or dumb. Dimensionality reduction is not just a blind or dumb mathematical exercise. In programming books, we tend not to emphasize the value. The point of dimensionality reduction is it's pattern recognition. And pattern recognition is learning. You have learned something about the external world. You have learned that there is luminosity has a certain relationship to the location in a much more simple way, right? This is an example. This is another example of dimensionality reduction. So now that we have the intuition for dimensionality reduction, and let me recap the two illustrations I gave you. One was what was the famous name of the alien? There was an alien movie in the West many years ago, very cute alien coming to Earth.
E.T.
Forget.
E.T.
E.T. That's right. So here is E.T. looking at the Earth, and one of the first understanding of patterns that it would recognize about human beings is human beings don't live in 3 dimensions. Approximately, to the first approximation, they live on the surface of the Earth, isn't it? And the crucial word is to the first approximation. You approximate it. So you say, even if people live there high up from space, you can sort of ignore these heights, and sometimes, so it is okay to approximate. In the case of the light, a dimensionality reduction need not have an approximation. It was a pretty exact thing. But for many situations, it is okay to do a trade-off, to trade in some exactitude in the data for a simpler reinterpretation of the data. When you do that, you are doing dimensionality reduction. So now, that is one. The other is the question of the light, lantern. Imagine that you have a kerosene lantern or a bit of lamp, and you are inside your tent, camping tent, and you're trying to figure out how does the light vary with respect to distance. After a little while, you'll realize that this thing can easily be written as this, a simpler table. Right? So that is classic pattern recognition. Now, how do we do pattern recognition? Now that we know what it is, let's go into the how of it. How. And it's a pretty big topic. There are many beautiful algorithms. The simplest of them is something called principal component analysis, PCA. PCA is one of those algorithms that is so intuitive and so obvious, in some sense, in hindsight, that it has been discovered over various periods of time by different mathematicians. It seems independently. For the longest time, it was ascribed to a bunch of French mathematicians to have discovered it in the 1960s or the 1970s. However, later, people who do the sociology of scientists or science, these are people who treat scientists as a tribe of people, anthropological study of scientists as a tribe, and their behaviors, tribal behaviors, they often worry that the real inventors real discoverers don't get credit. The credit always goes to the famous guy or for somebody in a more affluent country. And so there is something called, anyway, I'll give an aside. There is something, this particular discovery actually is very amusing in the, and I'll sort of take a digression and mention. It's called the Stigler's law of eponymy. Eponymy. Eponymy is when you say Newton's law, means the law is named after a guy named Newton. Or this guy, Moore's law, or whatever it is, many, many different things. So Stigler's law of eponymy says that a law or discovery named after a person is almost never discovered by that person first. It's a pretty profound, as a pretty astonishing statement about our STEM fields, about engineers and scientists and mathematicians. It's also a pretty harsh criticism of our field. But he has done, obviously, he is the great authority who has studied our STEM field practitioners as a tribe and found this to be more or less universally true. As many people have pointed out, a lot of the Newton's law were already talked about by Robert Hooke, a less known scientist. Calculus, which we ascribe to Newton, was already developed by Leibniz, and it was already discovered, it turns out, in medieval ages by it seems the Middle Eastern mathematicians. And now people believe that the roots go even older. It goes back to ancient Chinese and Indian mathematicians, and perhaps it goes even further back, all the way to Egyptian civilization. But it's very true. Stigler made a very interesting comment. He said, the proof of the Stigler law is in the law itself. So how is that possible? It's possible because, as Stigler very humorously pointed out, he didn't discover this law. It was his friend, Morton, whose permission he took to reinforce the point, who discovered this law. But Stigler said, you know what, let's prove it. I will claim that I discovered this law, and so it will be known. So Stigler's law of eponymy is actually Morton's law of economy, and therefore the proof of the law is in the law itself. So it is said. Now, very much in the spirit of Stigler's law of economy, actually, PCA, the earliest discovery that we find, is in an Indian mathematician who most people have never heard of, called Kosambi. Well, the father mathematician and son mathematician, but the one of them, the one who discovered it, is actually a lesser known mathematician. He was actually from my university, undergraduate university. I once went over to that university and asked the people, do you know anything about Kosambi? He made a lot of remarkable discoveries. At that time, India was still a colonial land ruled over by the Brits. And so access to scientific literature was scarce. Remarkable that he sat down there and discovered it. And obviously he published it. It isn't that he didn't publish it. But who cares for the writings of an obscure mathematician from a colonized land, third world? So his discovery actually was not mentioned, even though published in scientific journals. And it was attributed to some European, to some French mathematicians. And so I mention it as an anecdote about how our field goes. Many of you in your careers have often felt that you did great work, but the credit went to your boss or to somebody more famous who heard you say that, and so on and so forth. Well, that's Stigler's law of economy. Get used to it. So that's how it goes. But anyway, how is that relevant here? So I'll make the main argument for PCA, principal component analysis. But before I do that, let me mention that the state of the art today has gone beyond PCA. We have some beautiful algorithms, which I will not cover. It is called, so two which beautiful ones are key, and I leave this for you to read about, and UMAP. These are two alternative ones, but they require fairly high-end mathematics to understand. But principal component analysis is so simple that I hope, explain it to you in its entirety. So I've been saying I won't use math in this series. Today, I'll break that promise just a tiny little bit, because I feel that this could be a great way to show you how math actually makes understanding things intuitive and simple, actually. It never complicates things. It always makes it much easier to understand. So I'll argue it like this. And principal component analysis is quite closely related to linear regression. But and you may catch on to that. If you don't, that too is okay. But I will use correlation as an argument. So imagine that there is an entrepreneur who's trying to sell ice creams on a beach. You have amount of ice cream sold, Y, ice cream sold that the user has data, and the temperature on the beach. And let us say, in a very simplified world, the relationship, the entrepreneur has been gathering data and observes a pattern like this. Are we together? Now, this pattern we can simplify by scaling the data and going to the center of mass. So by just taking the coordinates to here, just translating the coordinates, I can put it to the center. So I'll redraw this same data. Do not be alarmed, it's the same data. I'll just move the axis to a different place. Like this. Now you have lots of data. What you're looking at is not the ice, like the temperature, but you're replacing a new temperature, T prime, which is T minus the average temperature, T average, right? The center, the average. You're just moving the axis. Likewise, Y prime is Y minus Y average. Just sitting in the center of the data. It turns out that if you sit in the center of things, you can get a much better view of data. Now, clearly, if I were to ask you, is there a relationship between temperature and the ice cream sold? What would be your answer? Is there a correlation between temperature and the ice cream sold? Let me call this X. Actually, well, let me just use T itself. T. Is there a correlation? What you have understood about correlation, what would you say? Anyone?
Yes, it is. There is a
Clearly,
correlation. There is. Yeah.
and it's a positive correlation. The warmer the day, the more California children go to the beach, and well, the more ice cream. Therefore, you are able to sell if you have a little ice cream shack on the beach. On the other hand, if it is a cold, wintry day, you're unlikely to sell too many ice creams because only some die-hard and brave souls will show up at the beach.
It's kind of translation invariant, actually.
Translation. Yeah, the data, I just translated it to the center. Yeah, the correlation remains. You're right. So now, if on the other hand, I were to tell you that, look at this data. If this was the data and sitting at the center, so this is the contrafactual. This is not what happened. Contrafactual. Suppose this was the relationship between, and I'll call this A and B. Contrafactual is that didn't factually happen, right? In our story. When you look at the contrafactual, would you say there's a correlation? There's any relationship between T and Y, ice cream sold and the temperature? If the contrafactual is how the reality presented itself, what would you say? No correlation, isn't it, guys? I'll appreciate if you guys please speak up. I would like this to be a little bit more interactive. There are quite a few of you here. So then the question comes, there is no relationship. On the other hand, here there is a relationship, distinct, positive, co-varying relationship, isn't it? So one is informative, the other just says the input variable and this data is non-informative. There is no relationship here at all. Observe something beautiful geometrically. I can wrap this up into a beautiful, perfect circle, isn't it, guys? I can shrink wrap this data into a circle. On the other hand, if I try to shrink wrap this data, it is not isotropic. It is not same in all direction. It shows a very strong directionality. Do you see that, guys? That situation A, if I shrink wrap that data, it has a very strong directionality to it. It is not what people call isotropic. It is not the same in all directions. Whereas situation B is isotropic data, the same in all directions. Whether you look north, east, west, south, it looks the same. Are we together, guys? Anyone?
Yes.
It is. And so now think about it this way. Those of you who are used to making pizza or used to making in the Indian culture roti, what do? You start with a round ball, round sphere, more or less, which is isotropic, same. And what do? You sort of compress it, isn't it? Till you compress it a little bit, it begins to look like a baglet. And then you compress it even a little bit more, and finally it begins to look like a desk. Right? The desk, the third dimension is gone. more or less, right? It is not a sphere anymore. It is a flat disk. Circular, but flat disk. Well, circular if you're good at making roti, or pizza. If not, some vague approximation to a circle. That's how I would make roti. Does that make sense, guys? Right. So whenever you take something isotropic, you have deliberately imposed a structure when you are making a baguette, let's say, or making a pizza or something. In the same way, you can say, with the same intuition, you can say that suppose data, this is not really true, but suppose this is the trajectory of the data. This is sorry, let me use a different color. Suppose this is what happened to the data. Somebody took this isotropic data and some force converted it into this baguette shape. This is an ellipse, right? Approximately, you would call this an ellipse. And this is a circle. The moment you convert a circle into an ellipse, the ellipse has structure. It shows a relationship between, for example, here, temperature and the ice cream sold, isn't it? Whereas a circular data, isotropic data, shows no relationship. The moment you compress or you sort of exert pressure on the circle and you sort of mold it into an ellipse, now there is a relationship. There is a correlation. Geometrically, guys, do you see this? And so you can ask this question, whatever transformation, let's say M, transformation, I'm deliberately calling it M, that made this circle or this disk of a data into this ellipse data, has that M transformation must be something that is aware of the relationship between temperature and ice cream, isn't it? That M, in a sense, captures the relationship between temperature and ice cream. So let us think about what that is. Now, when you look at this structure, let us see what are the characteristics of this structure, this ellipse. An ellipse has a major axis, you know, the axis, this axis, major axis, the direction of maximum spread of the data, the maximum variation or maximum spread of the data, the long axis, intuitively, it has one. And then you can talk about let me take another color. What could be a good color? Let me take this. There is also the minor axis, isn't it? Perpendicular to the major axis is the minor axis. And if you look at the data, what has happened is this circle, if you superimpose your ellipse on top of it, you would realize that this data has become this ellipse, it has gotten scattered. So every point of data, let's say this point of data, I'll call this point of data A. A has somehow, if you look at A, it has gone and gotten stretched out. Some other point of data B has been slightly rotated and slightly stretched out, right? So, and if you look at the fate of any point in this, now let's look at that. And this argument is actually the heart of it, actually. A principal component analysis, guys, is at the heart of a lot of biomedical studies, medical. It's probably one of the most popular method of machine learning used by the medicals, by the medical field. So it is worth understanding the intuition behind it. So what we are saying is that any point X P, which has a x and a y. Let's say this is the x-axis and a y-axis. It goes to another point, x prime, y prime, some point. So P, let us say P, in the ellipse, it has gotten rotated to this point. I'll just make an argument. Right? Something like that. Let us say something like this happened. You would agree that this can be explained as some amount of rotation along the origin, some rotation by theta, and some stretching. Some rotation
and shear. Yeah.
And some stretching or shrinking. The common word to them is scaling. Some scaling, right? That is it. Now it turns out that mathematics gives a tool to quantify it. It says that when x goes to x prime, then x prime, y prime, you do that using a matrix A, B, C, D. If you ever multiply a vector, a point, by a matrix, and this is a mathematical construct, a matrix, the matrix will move that point to some other place. Right? Matrix transforms a point to some other point. Right? Or intuitively, it moves that point from here to there, anywhere, right? Somewhere else. But when you apply the matrix to all of the points, and this is an important thing, a matrix M moves every point of our original disk to somewhere else, right? So every point here will go to X, like this relationship will go. This is the M matrix. And then comes a very interesting observation that there are certain points, let's say this point, let me color it green, this point, green point, this will only get stretched. It will go, let me call it P, P will go to P prime. It only got stretched. Likewise, this point only got stretched to, let me call this Q, it only gets stretched to Q prime. Likewise, a point here, R, only gets scaled back to R prime. And likewise, a point S here, it gets shrunk to S prime. They don't go through rotations at all. So in the principal axis, in the direction of the principal axis, all the points that fall along the axis in the original sphere, they only get stretched. It's a mathematical fact. And just stare at this and you can soon convince yourself that this does happen. Right? Now, the degree to which P gets stretched to P prime, let us say it gets scaled by a factor lambda 1. Right? Let's say 2, it becomes twice as long. Right? Likewise, the factor by which along the other axis, this point R and S are scaled, let us call it lambda 2. Now think about it. If I were to tell you only these facts, the direction, in the direction of the principal axis, let me call this vector E1 vector, and the direction of this other axis, call it E2. Convince yourself that if I gave you just E1 and E2 as a vector, two vectors, you would be able to draw the ellipse. You would know in which directions to point the ellipse. And if I also gave you lambda 1 and lambda 2, you would know how much to stretch the ellipse, the extent of the ellipse, isn't it? So these four things are sufficient to define or quantify the ellipse that shrink wraps the data. that shrink wraps this data. Would you agree, guys? Because all I need to know in an ellipse is what is this axis, what is this axis, E2, and to what extent a point which was in the original disk has gotten stretched, lambda 1 and lambda 2. If I know these things, I will be able to draw the ellipse, essentially. So I'll pause here for a moment so you digest this fact. Convince yourself that it is true, and if not, let me know and I can try to explain it again.
Can even an E2 boil down to just rotations, and lambda 1, lambda 2 are the stretches?
E1 and E2 are the directions in which
Directions.
Yeah, these are the principal axes of the major and minor axis of the ellipse.
So they are vectors, and lambda 1, lambda 2 are the stretches, the
The
scale.
degrees of stretches, yeah, the degrees of scaling. That's all. There is a name for this quantity. These things have a very interesting name. These are called in mathematics eigenvectors. And these ones are called eigenvalues. Remember, one is vectors, one is values, eigenvalues.
Gosh, this was like
And
30, 40 years ago, Asif. The eigenvalue decomposition of matrices.
right. And so, if you think about it, whatever the matrix did to the sphere, to the circular isotropic data, which was this transformation M, every transformation from a circle to an ellipse or in higher dimension, an ellipsoid, is represented by some matrix. And what I'm saying is, to say that the matrix M transformed this circular data to an ellipse is the same as to say that I'm giving you this information, eigenvectors and eigenvalues. So therefore, M is somehow equivalent to giving the eigenvectors and eigenvalues. The sum total information of M is nothing but this. And it turns out that there is a mathematical machinery that decomposes M in a very intuitive way, very obvious way, once you get the intuition. Literally, M can be written as U, right? A matrix U, a diagonal matrix D, and a U transpose matrix, and which is also an inverse matrix. But I'll just mention what is U. U is literally E1 and E2 vectors written side by side. This matrix. What is the diagonal matrix? It is nothing but lambda 1, lambda 2, 0, 0, the eigenvalue matrix, and this is U transpose is just the transpose of this, which means that suppose I write it as E1. So let me write EU. Let us write that the first E1x, E1y, E2x, E2 vectors y component. Suppose it is this, then U transpose would be the just written it, changing the rows and columns. E2x, E1y, E2y. And the remarkable thing is, this result spills out. The fact that you can do that is usually considered one of the advanced topics in linear algebra. It is rather unfortunate that it is taught in a very abstract way and most people forget all about it, because it is at the heart of machine learning in many, many ways. In particular, as I showed you today, it is very obvious and intuitive. It captures the actual relationship in a data. If the data is linear, if like this, if the data can be shrink wrapped in an ellipsoid, in an ellipse or an ellipsoid, then it means that it's relationship can be captured as a transformation matrix M, which has taken a disk, an isotropic, no relationship data, and molded it into, shaped it into the way you would shape or mold dough into a pizza or a roti. You can imagine that a matrix M has shaped that dough into the shape of the ellipse. And therefore, the true relationship between input, let's say temperature is the input, and the prediction, which is Y, can be represented here. Or it need not be prediction, it can just be facts. Data has an internal relationship. But when you do that, you're doing eigenvalue representation. Now observe in this eigenvalue decomposition. So I hope you understand this, guys. The fact that data like this can be shrink wrapped, when it can be shrink wrapped, it can be represented with eigenvectors and eigenvalues. And there is a matrix that contains that. Now you would say, now wait a minute. Did I not learn about an alternate way of thinking about this matrix using correlation? Remember, we talked about correlation. Correlation between T, temperature, and Y. Right? Actually, if I may, I just think of it as X and Y. Ultimately, I also have a correlation between tea and ice cream, temperature and ice cream. Doesn't that correlation capture exactly the same information? You would argue? Is that fair to argue?
Yes.
It is. So these are two alternate representations of the same reality. If there are two alternate representations of the same reality, then the two realities must be related. There must be a mapping from one to the other. And such a mapping does exist. In fact, M, in terms of the correlation, is literally this. It is, this matrix can be written as sigma xx, sigma square xx, sigma xy, the standard deviation between x and y, sigma standard deviation between, square of the standard deviation. This is what it is. It turns out that this matrix that transforms isotropic data into ellipsoid is literally built out of unscaled correlation. It's called covariance. The covariance matrix, right? M is literally the covariance matrix. And the eigenvalues of the covariance matrix point to how the ellipse will look, eigenvalue and eigenvector. So this is all very interrelated. Now, let me summarize what we talked about. We said that when we see a relationship like this, we can take a contrafactual and say, there was isotropic noise, which has no relationship. If I somehow treat that as a dough that you can mold into the data that we have, into the bagelet or the ellipse data that you have, then I need to, that which has induced relationship, you molded it into a relationship, there has to be a molding force, a molding matrix, M. That matrix captures the correlations or the correlations in the new data, transformed data. Therefore, it is made up of the covariance elements. And once you have that, you also ask this question, but once it becomes an ellipse, I can look at the principal axes and I can look at the amount of stretching along the principal or shrinking along the principal axis. And that is an alternate reality. And all of it is beautifully captured by this equation, right? And this you can say is actually the correlation xx squared sigma. This is the correlation matrix. This is the standard, just the variance. This is the covariance and this is the variance of it, a variable with itself, which is the square of standard deviation you're familiar with. So that is how all these beautiful ideas get stitched into a single mathematical representation. Isn't it simple? You see that how simply math brings it together. And that math is not mysterious, it is dead obvious. Now comes a beautiful point. Observe lambda 1 and lambda 2. When you look at this, lambda 1 has stretched the data along the principal axis, isn't it? It is a value that you expect probably greater than 1. But what about lambda 2? It has shrunk the data, compressed the data towards the origin, hasn't it? The lambda 2, like this point, has gotten shrunk towards the origin. If you were to, and I will just superimpose the original data as green dots. And so what happened to this point? It got shrunk down to this point. Do you see that, guys? Point P became Q. Capital P became Q. It got shrunk, pulled inwards. So obviously lambda 2, lambda 1 is greater than lambda 2. Is that true? Now, lambda 2, the shrinking in your mind, if you visualize and you say, you know what? Maybe lambda 2 is so small, it has shrunk it down so much that not much information would be lost if what happens if I set lambda 2 to 0? Right? Imagine the extreme case in which lambda 2 becomes 0 or very close to 0, almost 0. Then all the points, this ellipse becomes a very pencil thin ellipse, very long and a very pencil thin ellipse in which all the points have been collapsed onto this E1 axis, isn't it? This direction. Are we making sense? All of the points get collapsed onto the blue line if I make lambda 2 0. Right? If I shrink the points down to 0, down to no separation along the other axis, the minor axis, it would all collapse onto the major axis, all the points. And sometimes that is a good thing. You say, if I could do that, then every single point, now imagine this line, blue line, I will redraw the blue line, and all the points are now just sitting on the blue line, isn't it? What you are saying is that even though they are a little bit around the blue line, you ignore the value along the perpendicular to blue line axis. You only look at the value, and suppose this is the center. Suppose you call this the origin. So every point can be described by a single variable, theta, right? Which is the distance from, let me call this O, from O along the blue line. So what you're saying is I can take a point X and Y, right? Any point, if you look at this, go back to this, every point I could represent it as a X and Y point, right? Or given a temperature, given a ice cream sold, right? So Ty point, it's a two-dimensional point. Let me just call it X and Y. Right? X and Y point. A two-dimensional point, now I'm representing it with a single point. I'm replacing this with a single point theta value, which is where does that point fall along the major axis, along the blue line? Does it make sense, guys? Right? Do you see the intuition there?
Just becoming like a distance from the origin.
Simply distance from the origin. It just is the distance from the center of the blue line, positive or negative direction. And so this is again a case of dimensionality reduction, because this was two-dimensional data. This is a one-dimensional data. Now you would say, now wait a minute. you are going to say that you're going to represent data with only one variable, theta. What have I lost? You have lost the fact that uh, points are not exactly sitting on the blue axis. They're sort of hovering around the blue axis, isn't it? They're sort of flying a little bit in the air along the green axis. You lose that data. So you say that to the first approximation, they're sitting on the blue axis. And when you do that, excuse me, guys, I'll take a minute. I'm giving a talk. Yeah. So I apologize for the interruption. So what do we lose? You lose a little bit. You trade off a little bit of accuracy, but what you gain is simplicity. Now you can describe the data simply. Is it justified? It turns out it is often justified because when you look at data in lower dimensions, we develop stronger intuition about it. In fact, biologists, when they look at data from high, especially when you're dealing with data in 20, there are 20 factors affecting a disease. And you can reduce those 20 factors down to 2 dimensions. You can actually visualize those factors. Suppose you could take data which existed in 20 dimensions and you could reduce it down to a plane. And you happen to notice that all the people who have this kind of diabetes are sitting here and with all the factors, and here are the people who have a different kind of problem and things like that. Do you see that even though these are abstract axes, theta 1, theta 2, it suddenly begins to make sense. You feel, aha, all of those 20 factors, x1 all the way to x20, 20, somehow are working together so that their real effect can be described by 2 factors, 2 underlying factors, theta 1 and theta 2. And biologists then, and many fields, not just biologists, in every field of endeavor, people have used this, and they have often given it names. They will name it, they'll give it, they will have names that make their way into textbooks and so on and so forth, meaningful names. Right? So that is a form of pattern recognition. You took a very complex reality, boiled it down, did dimensionality reduction to lower dimension. And when you did that, you found some underlying factors or underlying variables to which now you can give some intuition, you can give it some name, and it sort of encourages understanding about the field. Right? So that is the value of dimensionality reduction. I started out by saying that human beings cannot think last time beyond 3 dimensions. We can't. Not only can we human beings not think, we don't even mathematically quite understand the behavior of higher dimensions. Higher dimensions are mysterious. If you tie a shoelace and I add a 4th dimension, the shoelace can be immediately untied. You create a knot in 3 dimensions, you go to higher dimensions and it can be unknot. Higher dimensional spaces suffer from the so-called curse of dimensionality, which means that everybody becomes alone. The distance between any 2 people is vast. Right? And not only that, if you take, for example, a 10-dimensional sphere and you uniformly distribute data in that solid 10-dimensional sphere, nevertheless, you will find that most of the points are hovering around the periphery on the outer shell. How is that possible? It goes against human intuition. You would say, what about all this space inside? And yet it isn't so. So higher dimensional spaces are quite mysterious. They go against human intuition. Even when we mathematically understand it, we see that these things happen. We are not able to wrap our heads around it. It beats intuition. So there is value in seeing whether dimensionality reduction techniques and bringing it to lower dimension elucidates the meaning of that data much better. So that is one reason to do it. Another reason is sometimes some of the dimensions are actually useless. For example, in the case of human beings, it is not of great value if you're looking from a million miles away to look at human beings in 3 dimensions. It is far better to say that one person is sitting there on the sphere in location Fremont, another person is sitting there in location San Jose on the globe, and so forth. That's a more meaningful location. So next time a friend asks you for location, try to give a longitude, latitude, and height above sea level to the person, and say, meet me here, and see how confused your friend will be. So it helps to be sometimes dimensionality reduction has many purposes. It helps understand data. So that was a simple introduction to dimensionality reduction. Now, principal component analysis is the oldest technique. As I said, it was discovered, to the best of my knowledge, in the early 1940s by Kosambi in still colonized India, and rediscovered at different points of time, which is very interesting considering that Kosambi's work was actually published in a Western journal, in a leading mathematical journal, and nevertheless it got overlooked. And later on, when other people sort of rediscovered it, they got credit for it. But I suppose the idea is simple enough that it admits rediscovery by a lot of people in many different fields. Actually, it was rediscovered by people in many different fields over the years. So but there are other methods which are far more sophisticated. TSNE, UMAP, they do nonlinear transformations of the data and then discover relationships and lower dimensional understanding. So people use deep words, big mathematical words. They'll use lower dimensional embeddings and whatnot, right? So how about I give you, without going into UMAP or TSNE, how about I give you a simple intuition to that? So imagine that you went to sleep, when you got into your bed to go off to sleep, and as we all do, we sleep between sheets. There is a sheet on top of us, there's a sheet below us. The sheet on top of us, and maybe there's a blanket there. But let's just take a sheet, it's summer, right? And on that sheet, perchance, there are certain bed bugs, God forbid. Now, think of it from the point of view of that bed bug or that dust mite. When the sheet was flat, before you got into bed, as far as the bed bug was concerned, the bed bug could see only a microscopic little space. To it, the world looked flat, the sheet looked flat. You got into the sheet and you are one big giant as compared to the bed bug. And you have, as far as you know, the sheet now is not flat anymore. It is all curvy and occupying 3 dimensions, right? But to the bed bug, locally in its little world, will the world look flat? Will the world look 3-dimensional? Or would the bed bug have no clue? It is still living on a 2-dimensional world. Any venture a guess? To the bed bug, it would still be the same old 2-dimensional world, the world of the sheet. It would not notice the curvature of the sheet. Now imagine that you could light up the bed bugs using some, let's say, ultraviolet light and some chemicals that you have sprayed on the sheet to illuminate the bed bugs. Now, the data exists in 3 dimensions. Where are the bed bugs? That data is not informative. But if you could recognize that all the locations of the bed bugs are drawing the contours of this bed sheet, isn't it? All of the bed bugs that are there in three-dimensional space, right, that have lit up in your fluorescent light or whatever it is, UV light, they actually, the data, if you think about it, they are actually sitting on the bed sheet. So they are drawing the contours of the bed sheet, isn't it? And suppose you did not know the bed sheet, but you just had the data of where the bed bugs are. A pattern recognition that recognizes the shape of the bed sheet, therefore, on which the data resides, is a valuable pattern recognition exercise, and it is a valuable dimensionality reduction, because now you need to draw the coordinates on the bed sheet. How much from one end of the bed sheet, long end of the bed sheet, and how much from the short end of the bed sheet, isn't it? Every bug can be positioned there, despite the fact that the bed sheet has curvatures, has been crumpled up and curved. So the data is residing not along a flat line, not along a flat plane, as principal component analysis would require, but along a much more complex surface. Nevertheless, it is still a two-dimensional surface. So there are technologies and there are mathematical tools in machine learning that actually discover such two-dimensional, non-linear curved surfaces. These are called manifolds. Manifold is just a fancy word for a higher dimensional bedsheet without creases. It shouldn't have ironed out creases. It should just be smooth rolling bedsheet. A smooth rolling bedsheet in a higher dimension is perhaps one of the closest intuition you can have that captures pretty much all that the big word manifold in mathematics has to say. But manifold is a core concept in topology, in particular differential topology. And some of you who have been exposed to higher mathematics may have encountered this term. The reason I mention this term, intuition, is when you read the literature of machine learning, especially some of the research papers, they freely use these words, embedding manifolds and things like that. And every time you hear an embedding manifold, think of a bed sheet, and you wouldn't be far off, or a higher dimensional bed sheet. So that is dimensionality reduction. So to summarize, dimensionality reduction is a part of pattern recognition. The other example we learned is clustering. And in this series, we learned two predictive modeling approaches. One is classifiers, one is regressors, regression and classification. And in pattern recognition, we learned about clustering and dimensionality reduction. I will end there. Machine learning has one more interesting area of quite importance these days called reinforcement learning, which is learning from rewards and punishments. But it's a topic of its own. I invite you to explore that. But for this series, our story ends here. Any questions?
Where would the
Sorry, go ahead. Sorry.
Where would the applicability of this? I can already imagine you mentioned about medical field, right? People could say normal cell size and a deformed in case of cancerous tissue. I can imagine that. What are the use cases for dimensionality reductions?
Oh, dimensionality reduction is so ubiquitously used. Hard to say so many things. I'll give you examples. In any data that you do, computations often become bizarrely expensive, right? So you always try to project it down to a lower dimension because computations are more manageable there. Not only more manageable, it gives you deeper insights. Almost every data that you get, dimensionality reduction should be one of the, it's like, you wake up in the morning, you brush your teeth. In the same way, whenever you get new data that you haven't seen before, amongst all the things you do, clean up the data, etc., you must do a dimensionality reduction exercise. Because if nothing else, it will help you visualize the data. Because all of our visualization libraries can help you. They all work in 2 dimensions and at most 3 dimensions. So you would need to get some intuition, some understanding of the data. That is just visualization itself. So dimensionality reduction comes in. The dimensionality reduction comes in also because you want to throw away the less important factors. Many things. So, for example, the stock price, let us say, of your favorite stock, right? In the AI community, it seems everybody is hung up on NVIDIA these days. Depends on many factors. For all you know, one of the factors may be how many penguins jumped off an iceberg into the sea that day. But you could plausibly argue that that factor, which may be somehow related to weather and which may somehow affect the mood of traders, is not really a very strong predictor of how the NVIDIA stocks would do. So you can sort of delete it if you're making a prediction model for NVIDIA stocks. Common sense, right? And the moment you elide that factor from consideration, you just reduce the dimensionality of the data by one. You threw away an unnecessary dimension, unnecessary feature. So that too is dimensionality reduction.
So you would call that as one of the options in data preparation, or it's becoming a de facto use during data preparation?
Data preparation and data analysis. The analysis of data is used it, and in data and in machine learning core activities also, because as you do the various, and when you register, when you take these courses, you will see here that we fluidly go from lower to higher dimension and from higher to lower dimension. Every time you go from higher to lower dimension, you are doing a dimensionality reduction. See, when people make, for example, amongst other things, let's say you have data X and Y, X1, X2, and you throw a few neurons there, and then you throw another 3 neurons, and then you have a prediction. Let's say that this goes this, and this goes. This is particular to neural networks, but I'll nevertheless mention it. You notice that signal is transforming, and I can keep going more and more. All the other things, this, forget it. So what are you doing? You took a 2-dimensional data and you have certain values coming out from each of these neurons. So you have projected it to a 5-dimensional space. Then you're using it to project it to a 3-dimensional space, and you're projecting it to a 1-dimensional space. So all neural networks are internally continually transforming data from one dimension to another. Because what it is doing is, it is trying to find the most meaningful representation of the data. And that meaningful representation of the data is also the search for the right dimensionality, the right space in which data is most meaningfully represented by that layer of the neural network.
Perfect.
So it is dimensionality change or dimensionality fluidity is the norm. It's at the heart of machine learning.
Thanks, sir.
Any other questions, guys?
Not a question,
Yeah, go ahead.
Not a question, but observation.
Go ahead.
It's from many years. We did all computations in a parametric space that was 2D, U and V. And the idea was to model surfaces, NURB surfaces using that. So
That is very true, coming from your Autodesk background. Yes, very much true.
coming to
You do it.
surfaces and cylinders or any class one surfaces for automobiles and all that. So what we found
Yes,
out is that the geometric splitting surfaces, merging surfaces, rounds, fillets are very easy to be done in 2D and then take them to 3D.
absolutely. Thank you for sharing that example. Very much true. So you do this surface modeling in 2 dimensions, parametric space, even though you know that reality is in 3 dimensions, because it helps you represent it much better.
Thank you. But this was interesting. I mean, I slowly getting it, but definitely a magic box. How dimensionality is kind of reduced, and so is there a is these algorithms kind of figure out what is more what dimensions matter more, and in which dimensions the data doesn't vary more? It's
Yes,
kind of
yes, it does. In fact, see, guys, and this is a good way segue to my conclusion. Can you imagine that a bucket of sand has been transformed into machines which are amiable to the kind of mathematics which, when applied to large data sets, can do all of these things, can understand and discover these patterns? That is the great beauty of this subject, machine learning. See, machine learning, AI, undoubtedly is the biggest revolution of our lifetime. It will be long after 1,000 years from now, when the history of the sciences are written. In my belief, it will be at least tantamount to the Industrial Revolution itself, if not dwarf the Industrial Revolution in its impact and scope. This is the biggest thing that's happening. The world is changing all around us. I remember a phrase from a TV show I used to love, being a science geek, called, there's a lot of drama and popularization, but still a really nice one, called Person of Interest. Anybody remembers that TV show, Person of Interest? If not, just watch it. You might enjoy it. So, in the Person of Interest, one great scientist has created AGI, the machine, and it's helping the US government find troublemakers. So he makes a statement. He looks around and he says, the world has changed completely. People just don't know about it. What was fiction a few years ago, 15 years ago, is fact today. The world has profoundly changed. The nature of job has changed. Everything has changed, but it is all happening in slow motion. And people are just not aware of it. They're continuing with their lives as though nothing has changed. But that is the great lesson of history. Throughout history, transformations, change is afoot. Yet, at any moment in time, every culture, in every civilization, people feel that the world will remain exactly the way it is. It never does. It's always changing, but in our current world, with AI coming, the change has accelerated and it has become deep and profound. So be ready for it, guys. Learn AI, learn machine learning, because without it, you will look rather antiquated. You need to learn this field. It's the new literacy. Just like when motor cars came, to not know how to drive would handicap you. In the same way, when computers came, and not to know how to use a computer would handicap you, today, no matter what discipline, what field of endeavor you are in, to not know AI, to not know machine learning, will handicap you. It is a new necessary literacy to know AI. With that, I will end our recorded session.